Okay, in this lecture, we're going to now discuss how to integrate the natural logarithmic function. In the previous lecture, we learned how to differentiate these functions. So the rules are pretty simple once you know how to differentiate, because again, we're just going in the opposite direction now. So if u is a differentiable function of x, then the antiderivative of 1 over u is equal to natural log of u plus c, absolute value of u. The reason why there's an absolute value here in both cases is that, as we observed last time with the theorem stating the derivative of a natural log, that both both u and absolute value of u have the same derivative. So when we're looking at possible antiderivatives of 1 over u, we have that the absolute value is there. So let's just, again, this is going to be a very straightforward lecture in that this is our theorem, and we're just going to integrate a bunch of examples. So let's start with something simple. So let's look at the integral of 2 over x dx. Okay, so as with antiderivatives or integrals before, we can take out the constants, and then we just have 2 times this indefinite integral, and if we apply this theorem, we see that this is twice natural log of absolute value of x plus c. So that's pretty straightforward application of this theorem. Let's look at something a little bit more complicated now, but not much more. So let's say we want to look at the indefinite integral of 1 over 4x minus 1 dx. Okay. So here we can just use some change of variables. This is something that we've done quite a bit in one of our lectures. So we just say let u equal 4x minus 1, which means that du is equal to 4 dx. Or in other words, 1/4 of du is equal to dx. So again, the goal with change of variables is to replace every x by some form of u, including dx. So there's our u, and then dx is 1/4 of du. So now we can just interchange those. That's 1 over u, and then dx is 1/4 of du. And now that's just some constant number. We can take that out, and we get 1/4 of 1 over u du, which we apply this theorem here, and we get that this is 1/4 of the natural logarithm of the absolute value of u plus c. But again, we were asked to integrate with respect to x. There are no x's here. We need to plug back in what u is, namely 4x minus 1. So then this becomes 1/4 of the natural log of absolute value of 4x minus 1 plus c. Okay. So again, provided that you are very comfortable with change of variables, U-substitution, standard integration techniques, natural logarithmic functions in 1 over u and 1 over x, these things are not that much more difficult. You just have to memorize these theorems. Okay. Now, as before, when we were looking at not antiderivatives, when we were looking at definite integrals, and we did change of variables, we had to make sure that our limits of integration matched up. And I think the following example will be a good illustration, a reminder of how to do that. So because I'm going to need some room, I'm going to erase here. I might end up going to the other side. Okay, so suppose we want to find the area of the region bounded by the graph of, say, x over, so y is equal to x over x squared plus 1. The x-axis and the line x equals 3. Okay. So basically the picture, I don't even know what this function looks like, but it is, just looking at it, I can tell that it's non-negative. I should probably say lines x equals 3, x equals 0, so the y-axis. Okay, so on that interval there, this is indeed a positive function. It's above the x-axis, so we can interpret the definite integral as the area under that curve. Okay, so let's look at the solution here. We just know that the area is going to be 0 to 3 with x over x squared plus 1 dx. Okay. Now, because all of you are data science majors and you have access to nice things like Jupyter notebooks and plotting, it would help just to plot that, just to make sure, get a sense of what it looks like from that on that interval, and verify for yourself that indeed the area is well defined. Okay. So now that we've set this up, how do we take this integral? Well, we need to use change of variables, or that's one way to do it. So we can say, let u equal x squared plus 1, and then we see that du is equal to 2x dx. So that's u, and then I see x times dx, but there's an extra 2 there, so I can divide by 2 on both sides and get that 1/2 of du is equal to x dx. So then x dx is 1/2 of du, 1 over x squared plus 1 is 1 over u. We're good, but we need to make sure that our limits of integration now go to u instead of x. So what is this area equal now? So when x is equal to 0, u is equal to 1. When x is equal to 3, u is equal to 10. So then we have 1 over u. So that takes care of this piece there. And then we have x times dx, which is 1/2 of du. Okay, so if we take that constant out, we get 1/2 of definite integral from 1 to 10 of 1 over u du. Is that correct? Yeah. So then this is equal to, I'll write it up here because I have the room. This is equal to 1/2 of natural log of absolute value of u from 1 to 10. Okay, so then this becomes 1/2 of natural log of absolute value of 10 minus natural log absolute value of 1. But that is just 0. Natural log of 1 is 0, so it's just 1/2 natural log of 10. And whatever that becomes there. And that would be the answer for that problem there. Okay. So again, it's just applying this theorem and just remembering all the techniques of integration that we've covered in previous lectures. Okay. Now, there is one technique that we haven't touched on much that I should probably mention. And that is a long division. So suppose we want to look at, say, the indefinite integral of x squared plus x plus 1 all over x squared plus 1 dx, right? Sometimes you will encounter things that look like this. Now here, we see that for x positive, like this is algebraic, well, not even x positive, just algebraically, this is a larger term than here, so we can use long division of polynomials to simplify that. So how does that work? We'll just like note that we want to divide that into this. And in previous lectures, when we've looked at integrating things, we've learned that that simplifying what you're integrating first and then taking the integral is the best way to go. So when we could possibly factor and eliminate terms, that helped us. Here we can't factor and eliminate any terms, so another technique we can use is just to divide this into that and see what we get. So what does this look like? So how many times does this go into this term here? Well, it goes into it one time, right? The highest power there's 2, highest power there's 2, that goes into that one time. So then 1 times this expression, you get this, and you subtract off that term, just like normal long division. So now x squared minus x squared is 0, x minus, there's no other x, 1 minus 1 is 0, so you're left with this. Now x cannot divide into, x squared cannot divide into x, so we stop, and we see that our remainder is that divided by that, just like normal long division. So what does this integral equal? It's equal to 1 plus the remainder, that divided by that. Okay. So now that we've simplified it, we can break this integral up into its pieces. So this is the integral of dx plus the integral of x over x squared plus 1 dx. So then we have x plus some constant 1 for this piece. And then here, if I'm using more scratch work here, if u is equal to x squared plus 1, then du is equal to 2x dx, which means that 1/2 of du is equal to x dx. So 1/2 of du is equal to x times dx. So this is just, I forgot my half of 1 over u du. plus C1 plus 1/2 of the natural log of U, absolute value, the U is x squared plus 1. Some constant 2, but constant plus a constant, you just add them to some constant C. And that would be the final answer there. Okay. Okay, so we should also remember all the trig integrals and antiderivatives. And this, now that we know how to find these 1 over something integrals, we can use that to find, for example, if we look at the integral of tangent x dx. How? Well, we recall the definition of tangent as being sine divided by cosine, right? Right? So now we can use U-substitution and or change the variables and let U equal cosine x, and then du is equal to negative sine x dx. And then we see sine x dx, so that if we're trying to eliminate all x over here and replace it with the variable u, we get that negative du is equal to sine x dx. So then we can replace everything here in terms of u. So if there's I'll just write it out. So this is 1 over u times negative du. Take the negative out. Oh. So that'd be negative natural log absolute value of u, but what is u? It's cosine x. And then don't forget your constant of integration. Okay, and there is a whole table of antiderivatives of the trig functions in this section. This is actually section 5.2. That you're gonna want to look up and have on a little sheet when you're doing your homework problems. And with that note, I should probably give you some homework problems to look at from this section. Say 5 through 17, 29 through 37. Yeah. Those should be good practice for applying this theorem over and over again until you do not forget it. Okay, so that'll be the end of this lecture now.